Hello viewers, we will discuss the conversion method from multiple integral to single integral. So interesting conversion method. Before discussing it, we memorize the Leibniz theorem for differentiation under the integral sign. Now the integral with lower limit a of x and b of x is the upper limit. G of x comma t be the integrand, and with respect to t we integrate this term. Now differentiate with respect to x. What results? It's already seen in previous lecture. So we use this formula g of x comma bx ddx of vx minus gx comma a of x, that's the lower limit a of x, ddx of a of x plus a of x to b of x, partial differentiation x comma t dx and dt. This is the Leibniz theorem, very interesting theorem. If this theorem apply to a such example, that's a2x x minus t ut dt and the derivatives with respect to x, then what results we'll get? Here we seen that x comma b of x, that means x comma upper limit, that means g of x comma x. So putting this value in x comma x, that means t is replaced by x, then the value of x minus t is 0, so the whole value is 0, so this is 0. And the derivation of lower limit, here the lower limit is constant, so derivation of lower limit is 0, so this is 0. And the third term would be written as a2x, and derivation of these terms with respect to x, that means derivation of x minus t with respect to x, we get this is 1, so u of t dt. Now integrating on the both sides with respect to x, then we get integration x minus t a2x u of t dt in left side, but right side there are two integral sign ut dt, and this is a2x, this is a2x, but there are two integral signs, so in two integrating variable, that means taking this is x on, so this upper limit is x on, otherwise we cannot integrate with x on. And last integral upper limit is x, so this function represent with x, so these two are equal, that means this is the relation between second integral to single integral. So interesting. So now we'll discuss the generalized form of multiple integral to single integral, that means n integral in right side, then single integral to a left sides, with derivative the general conversion rule. For derivation of general conversion rule, we choose a function in of x equal to integral a to x x minus eta and power n minus 1 and a pop eta d eta. This is the considering function such as where eta is the positive integral and a is the constant. So we take this is the z of x comma eta, differentiating both sides of this, then we get d I of x, that's dx, equal to the upper limit putting in these terms, that means eta is replaced by x, then this value is 0, so this is 0, and since the lower limit is constant, so this is also 0, and third term is the a to x, the limit, the derivation of these terms with respect to x, then we get n minus 1 x minus eta power n minus 2 a of eta d eta. So we arrange it n minus 1 a to x, x minus eta n minus 2 f of eta d of eta. Since I n of x equal to this, so the power is n minus 1. When here n, when n minus 2, then we can write here n minus 1. So we can write it I n minus 1 of x. This is a very simple. Now we differentiating on the both sides again of this function. So again we differentiate these terms, then we get the second differentiation as this equal to n minus 1 I n minus 1 x with respect to x variable, must be differentiation term in exist here. If I n differentiate with respect to x, then the result n minus 1 I n minus 1 of x. These results can be applied in this here, in this. So we get n minus 1 into n minus 2 into I of n minus 2x. These results will be applied in here. So if we differentiate third terms, then we get this is x cube I n of x equal to n minus 1, n minus 2, n minus 3, and I of n minus 3 of x. And continuing this, so we get an interesting results if we derivating m terms. So we say that the differentiating m times we get the results, that means dm dxm I n of x equal to n minus 1, n minus 2, n minus 3, and last term is n minus m and I n minus m, where n greater than n. If we see the previous terms, then you see that when the second derivatives, then I of n minus 2, and then third derivatives, then n minus 3. So m derivatives, then n minus m. So easy that's term. At a particular case, that means we can write m equal to n minus 1, that's in a particular case, then m equal to n minus 1, then n minus 1 dx n minus 1 in of x equal to what's the results, n minus 1, n minus 2, n minus 3, and putting in here this is 1, so the previous term is 2, then the previous term is 3, and I of 1 of x. This is Masdi function of x. So this can be written in short form. This is the factorial of I on x. We know that the I n of x equal to a to x minus eta power n minus 1 a of eta d eta. So I1 of x equal to putting the values of n in here, then this the power is 0, so this is the 1, so integrating a to x a of eta d eta, so I1 equal to a to x a of eta d eta. And similarly we can write that if I2, we can write I2, that means the derivation of these terms in here, so we putting that dn dxn I n of x equal to n minus 1 factorial and di on dx of x. And this result is only f of x. That means d of ion of x and dx is only f of x. So, and we replacing the values of n equal to 2, 3, 4, and we get an interesting results when we putting the values of 2, then d square dx square I2 of x equal to 2 minus 1 factorial, that means 1, so we cannot write it, and this is only f of x. So integrating on the both sides, so we get I2 of x equal to integrating symbol and f of x dx. This is dummy variable, so we can sense it. This is x1, so the integrating limit a to x, the result is sensed in x, but this is the x2, then integrating variable is x2, and the last result depend on this a to x, so the result in a to x. So the results in terms of x. Similarly, we find the I3. What's the result of I3? If we can write in here n equal to 3, then the third derivatives ion of x equal to factorial 2 and f of x. So we can write it simply from here. That's the result is this is the 3, so I3 of x equal to integrating sign, there are 3, so f of x dx. Now we can change the dummy variable x1, so result a to x, but we can integrate is with respect to x2, then it is x2. So now a to x the another limit, and if we integrate x3 then limit is 3. So the last integral limit a to x, so the result is represented in terms of x. If we use this for the n, so in of x equal to n minus 1. Oh sorry, this there here are 2 factorial, the n minus 1 factorial, and integrating n times, that is f of x dx, then the dummy variable sense, and a to x the limit if we integrate with the x2, so this is the x2, and the previous limit a to x, if we integrate with x3 then this is 3, and the last result a to x must be, but the here the previous a to xn, that means the integrating variable xn. We see that this is the single integral, that means a to x minus eta power n minus 1 f of eta d of eta equal to n minus 1 factorial, and integrating limit a to xn, and a to x3, a to x2, f of x1, d of x1, d of x2, d of x3, dxn. So this is the relation between the multiple integral to single integral. We write an example for clearance of it as a multiple integral to single integral. Now please look at the question. 0 to x and 0 to x1 with the limit u of x2 dA of x2, and the result in here x1, so integrate with respect to x1. So what's the result in single integral? Here we see that there are two integral signs. So if we rewrite the results, that means 0 to that means a to x, x minus eta n minus 1 and n minus 1 এর factorial f of eta d eta equal to, there are n integral sign, that means a to x and a to xn and a to f of x1 dx1. So this is, we can write that x2, so integrating limit x2, and this is x3, then integrating variable x3 and xn. Here the integral sign is n, the number of integral sign is n, the integral sign is 2, so the two integral sign there are, so we can say that n equal to 2 in here. So if we rewrite this in this is, so 0 to x the limit, and x minus eta, x minus eta power 2 minus 1, that means 2 minus 1 এর factorial and f of eta d eta. So these results can be written as 0 to x minus eta and power is 1 f of eta d eta. That is very much interesting. There are a single integral and there are a multiple integral. So now we see that's another example of